Of course, we're going to be working through the problems from Greg's notes, a few of them at least. And so they're not, the notes haven't been printed out, so I mean, if you have it on your computer and you want to look at them, feel free to do so. If not, I'll be writing everyone that we do on the board. And so there's a lot of different problems in these notes, and we'll only have time to go over a decently large but not complete subset of them. So I think we should just get started as quickly as possible. So the first thing that we're going to be going over are a few of these sort of estimates he required in proof of the existence of the curve that come from complex analysis. Yes? Oh, good question. Yeah, so I guess I'm Brent Wers, one of Greg's students at UChicago, and yeah. So yes, I'm TAing this. Thank you. All right, so well, let's dive right in just for the sake of time. Now, the first thing we're going to do is we're going to prove a couple estimates using the complex analysis theorems, the distortion theorem, and the Beaver-Box theorem. And so first I'll remind you of the distortion theorem. This is sort of one of our main complex and analytic tools. And it's a theorem about these Schlicht functions that came up. So if we have f, so it's a map from the disk into C. This is so holomorphic, injective, and satisfies just some normalization criterion that f of 0 equals 0 and f prime of 0 equals 1. So these are the Schlicht functions, and if you have such a function, then we can perform the following bound on the derivative, which is if you look at some point, so f prime of z for some point in the disk, this derivative is guaranteed to be less than or equal to 1 plus the norm of z over 1 minus the norm of z cubed. And it's always greater than or equal to 1 minus the norm of z over 1 plus the norm of z cubed. So it sort of tells you that as you head towards the boundary, even if you're getting sort of infinite, you can't do it much worse than this sort of power growth you have going on. And so this is just a complex analytic fact. We'll just take it as a given here today and sort of derive some important bounds for us from this. And so the first set of bounds we're going to derive from this are the exercise 4 from his notes. So also, it's kind of confusing because exercises start with exercise 4. There are no exercises 1 through 3. But this is the first exercise. And it's so it's, to a certain extent, it's just taking the distortion theorem and producing a weaker but more easily usable one in the case of the upper half plane. So suppose f maps the upper half plane into C is holomorphic and injective. So suppose we have that. Then we can produce the following bound. So then sorry, I almost put something out of the order here. So we need to say there exists some universal constant that doesn't depend on your function at all, such that for all f of this form, and for any s in 1/2 up to 2, we have that f prime of I s y. So the derivative at some point along this line, with imaginary part, along this line with real part 0, we have that's less than or equal to some universal constant times the derivative at iy, and greater than or equal to some universal constant times the derivative at iy again. So sort of in the picture, what this is telling you is if here's your upper half plane, and you have your favorite point iy here, if you can sort of understand and control the derivative at this point, then for everything sort of nearby up to a multiplicative factor, so everything along this line here from 1/2 iy up to twice IY. All of these have a derivative that can differ by at most some universal multiplicative constant, universal over all functions. So that's the first part of the problem. And I guess I might as well write it up here now. The second part, so this gives us good control over varying the imaginary component of our function. But what happens if we move along the real axis? And that's what the next form of the estimate is that if you have f prime at some point, and it's written in this kind of bizarre looking form, so xy plus iy. So if you look at the point there, and this is less than or equal to some universal constant times x squared plus 1 to the rth power times f prime of iy, and it's greater than or equal to the same thing inverted. X squared plus 1 to the minus r times f prime of iy. And so what this is telling you again is that if you have your upper half plane, you have your favorite point iy, then as you go sort of this way, and the amount that you think about you're going that way is scaled by your height. That's why it's written as x times y. Then you have this sort of power law in x growth or decay of your derivative at worst. All right, so these will both be fairly easy corollaries of the distortion theorem, but I think that it'll be easiest to sort of approach this problem if we sort of use the following intermediate claim. This intermediate claim will come back and help us again later on in the problem set as well. And so I guess it's something that looks a priori perhaps even weaker than what we're trying to prove, but it'll turn out to be useful. So again, there's going to exist some constant such that for all f of the kind we're talking about, so for the upper half plane into C. So if we have such a function, then if you have 2 points, W and Z, that are closer together than 1/2 the imaginary part of, say, Z, that implies we have the same sort of relationship. So f prime of W is less than or equal to f prime of Z is less than or equal to some constant again times f prime of W. And so this will be what we'll use in the following couple of exercises. So the picture here, I guess, is something that should be included. So if we're in upper half plane now, and now we're fixing 2 points, W and Z. So you want to sort of think about Z being fixed first here. Then this condition that the distance between them is less than or equal to 1/2 the imaginary part of Z just means that you're in this ball here of radius 1/2 the imaginary part. And so for any W pick inside this ball, we have that the derivative is on the same order up to multiplicative constants. All right, so this will be our goal. And does anyone sort of see a good first step on trying to use this distortion theorem here about maps from the disk into C to prove this fact about these injective functions f from the upper half plane to C? Oh yeah, and I forgot to say these are also holomorphic injective. All of our functions are like that, essentially. So does anyone have a good first guess? Yes, that would work well, but it would take a lot of algebra. There's actually a simpler way to find the ball, to build a function that's injective on some ball. So it's sort of a neat trick, but yes, that method would work very well. But the simpler way is just to say, restrict to this ball of radius imaginary part of Z. This is a perfectly fine ball, and it has a perfectly fine injective holomorphic map on it, namely just the function f you're starting with restricted to this ball. And so that's something that, at least after rescaling and reshuffling it a bit to make it satisfy the conditions of that theorem, will, well, satisfy the conditions of the theorem, then you can apply that and just see what happens. So let's see how to prove that then. Just write that down formally. So we have this ball of radius mz about z. And we want to sort of make that the image of a ball of radius 1 about 0. And then compose it with f, and then normalize it to get a Schlicht function. So we're going to take our point f. We have a ball centered at z, so it's z. Plus then we want to have some, well, I'm going to be defining a function, call it g of w. So w is in the unit ball. And we want to make it so that it's this ball of radius imaginary part of z around z. And so to do that, you shift by z and scale it up by imaginary part of z. And then that times w. So this gives us our ball centered around z of radius imaginary part of z. Now we want to satisfy these conditions of the Schlicht functions. So we want to map 0 to 0 and have derivative 1 at 0. So if we see where 0 goes here, it goes to f at z. So we should subtract off f at z. And then we should go through and normalize it to have derivative 1 at 0, which, well, the derivative of what we have currently is imaginary part of z times f prime at z. So we should divide through by that. Times f prime at z. All right, and so this function, by our construction, you start with a unit disk, you map it to this disk here, and then you apply f, and then shift the result back to the origin, so it maps 0 to 0, and scale it so that the derivative is 1. So this is now a Schlicht function. So by our theorem, we can just write down a condition on the derivative of this g. So we see that the derivative of g at 0, at some point w, is less than or equal to that bound we have over there, 1 plus norm of w over 1 minus norm of w cubed, and it's greater than or equal to 1 minus norm of w over 1 plus norm of w cubed. Okay, so we have this bound. And now the important question is, what does this condition here, w minus z less than 1/2 mz, mean about this w down here, this w in our original unit ball? Well, so our balls of radius mz, we have w minus z is less than or equal to 1/2 mz, so the w down there has to be within what ball? In the sort of starting disk? Yeah? All right. Okay. Well, it's pretty easy to see that it has to be within the ball of radius 1/2, because I mean we just blew up everything, scaled it all by this factor mz, and so now it's all within that one ball of radius 1/2. So that means that all these norm w's here, so by our scaling, this w is such that norm of w is less than or equal to 1/2. So we're only looking at this ball of radius sort of half the original thing. And so that means everything here, we can just sort of make everything as bad as possible, on the range between 0 and 1/2. And both these bounds will be worst at 1/2. And if you just go through the algebra, you can see that this will imply that g prime at w is less than or equal to, this becomes 12, I believe. And the other side becomes something else, but it's something else that's not as bad as 1/12, just so we have a nice symmetric thing like we're trying to find. All right. So this gives us our control on the derivative of g. It's always bounded between these universal constants for any function f that we started with, and any w in this ball here. So now we just need to translate that back into conditions on f itself. But well, if we just try and calculate the derivative of g is this combination of functions of f, so we get a up here we get a, well, what do we get? We get a imaginary part of z times f prime at z plus mz times w. I guess this is all inside an absolute value. And then they're dividing by that thing on the bottom there, which is imaginary part of z times f prime at z itself. OK. So these imaginary parts just vanish from the calculation. They're not really part of it. And then we can multiply the entire equation through by this absolute value of f prime of z. And we conclude that 1/12 of absolute value of f prime of z is less or equal to, so the absolute value of f prime at z plus imaginary part of z times w, less or equal to 12 times f prime at z. All right. And so it's written a little bit differently than how we started because of this thing on the inside here, because now w for us is instead of being something within 1/2 imaginary part of z around in that ball around z, it's actually in that ball of radius 1/2 around 0. But those conditions are, I mean, they're clearly equivalent, right? If you had something of, of norm bounded away from 1/2 here, it just becomes something of norm bounded away from 1/2 mz away from z itself. And so this is just exactly our initial claim. Right, is that good? OK. So this is sort of our side claim. This is the one to keep in mind, which is that if you have two things and one's within the ball of radius 1/2 mz around the other, then their derivatives differ by at most a factor of 12 if you want, or just some absolute constant. And now we're going to be able to use this just to get the two desired facts from exercise 4. So for the first part, we wish to show that when s is between 1/2 and 2, f prime of isy is less than or equal to constant times f prime of iy, and it's greater than or equal to some, this should be, sorry, constant inverse there, the same constant inverse times f prime of iy. Well, so if we look at where isy is in comparison to iy, because s is between 1/2 and 2, sort of either isy will be in the ball of radius. So, OK, let me write this down rather than just saying it in words. So we want to show that there's some constant c such that c inverse of f prime iy is less or equal to f prime isy, so that's equal to some constant times f prime iy again. And s here is between 1/2 and 2. So in a picture, here's iy. Then somewhere along here, this little line segment I drew over there, we have siy. And so we want to say that these two things don't differ very much in the value of the derivative up to some multiplicative constant. And we'll use this claim. So I guess rather than just sort of, I don't know, rather than belabor the point too much longer, so if you look at the point iy, well, look at the point siy in this case. It's up here above iy. If you draw the ball of radius 1/2 siy about it, it's like this. And iy will be contained within it. So I guess I'm saying if s is in the interval now 1 to 2, so this upper part, then by our claim, we have that, well, iy can only differ from it by some multiplicative constant. So we have c inverse of f prime at iy less than or equal to f prime isy less than or equal to c times f prime of iy. So if s is between 1 and 2, the picture looks like this. Putting a ball around the point SIY will include the other one, and then we can just conclude what we want. Now there's a slightly different but very much related case, whereas if you're in between 1/2 and 1, so if you're somewhere in that lower segment, well, in that case, just put your ball around IY itself. It's going to be like that. And now this point ISY is there, so by applying our claim, we have that. So this case implies this case implies that C inverse times F prime ISY is less than or equal to F prime of IY is less than or equal to some constant times F prime ISY. And now this sort of looks a little bit backwards because you want to have your ISY in the middle, but then just notice that this relationship is symmetric between the two things involved in it. So we could equally as well rewrite this as saying, so we have F prime of IY is greater than or equal to, I'll just keep this here, C inverse F prime ISY. But now if we sort of regard this F prime ISY as being this one over here in the inequality, this second term, then we can say this is actually greater than or equal to C to the minus 2 times F prime of IY. And so then you can just multiply through by C and everything gets done. So you get that C inverse of F prime IY is less than or equal to F prime ISY is less than or equal to C times F prime IY. So that's the first part. All right. So now there's this second one where you try and take into account how things change with x. So we have this. We want to show that there exists C in R such that C inverse times x squared plus 1 to the rth power times f prime of IY is less than or equal to f prime at xy plus IY, which is less than or equal to C times x squared plus 1 to the rth power times f prime at IY. And we're going to want to use the same basic claim here, the one that when two derivatives are in this same ball of radius imaginary part, whenever they sort of share a ball like that, the derivatives differ by at most a multiplicative constant. And so I guess I'll give you the method that doesn't work first, and then give you a few moments to think about, see if you can come up with a method that does. And so both the method that doesn't work and the method that does, we'll try and connect these 2 points, IY and XY plus IY, by a series of balls. And so here's the method that does not work. So just for simplicity of drawing pictures, I'm going to just assume y equals 1. You can always do that because you could precompose by scaling, and it would just come out to the same factor in every term in the derivative. So don't worry about that. I'll just assume y is 1. So y equals 1. So that means we're trying to have the point I here. We're trying to connect it up to the point, which will be x plus I. And that's actually the reason that he writes in this funny way as xy plus iy, is because he wants to be able to scale it so that y is 1, and then just be left with x plus I. And so if you want to connect this thing by balls, all of radius sort of 1/2 imaginary parts, so balls of radius 1/2, the wrong way to do it is like this. So I think he drew this picture in lecture. But just sort of as a reminder, is to take balls all of the same size along the real axis like this. So each one of these balls is of radius 1/2, now that we've normalized y to be 1. And so the total number of balls here, so number of balls, is, well, it's about, it's 2x, I think. Something like 2x, or something of order x at least. And so then if we try and prove this by repeatedly applying this claim here, what happens is each time you try and move one ball along, you multiply by an extra factor of c. And so this will give you a bound of the following form. It'll tell you that f prime at x plus I is less than or equal to c to something like some constant to the x times f prime of I y, sorry, just of I, and is greater than or equal to c to the minus x times f prime of I. So it would give you some bound that was essentially exponential of order instead of the power that we're looking for here, this x squared plus 1 to the r. And so we need to do something more clever. And so you're gesturing with your fingers. You're saying go up and then.
Go direct up until you're at x, and then go one step to the side and go back down.
Yes, that's exactly correct, yes. So I'm going to require a slightly bigger picture, so I guess I'll say this is bad. So the correct thing is, as you said, go up, go over, then come back down. So we have the point I here. Go up to height x, which is up at I plus, so this is I times x, say. Move over here to x plus I times x. Then down here to just plain old x plus I. And so the reason for doing that is as you head up, the balls that you get to deal with become much, much larger. So you require fewer of them for these sort of side-to-side motions than you did here. So if we try and be sort of explicit about it, here's a ball of radius. This is a radius 1/2 x. Then down here at sort of, so this is up at level x. Down here at level 1/2 x, we then put another ball. And so it'll overlap the previous one. Now we keep going, 1/4 x. Put a ball. Down here's 1/8 x. Put a ball, and so on, until finally the ball that you're dealing with includes the point x plus I. So now the question is, how many balls did it require to do that? And so when can we guarantee that x plus I is contained in these balls? Well, sort of look at where our balls are centered. So our balls are centered at things of the form 1/2 to the k times x, where k is the index of the ball that we added. So we started off, I guess, with the 0th ball up here, and then we moved downwards. And so as soon as our center is below x plus I, so as soon as 1/2 to the k times x is below 1, then we'll know that the k balls, as drawn, will contain x in their union, x plus I in their union. Right, so if you take this one contains everything down to 1/2 x as soon as you take your first ball. With your second ball, you contain everything down to 1/4 x, and so on. And so after k balls, you contain everything down to height 1/2 to the kx. And the thing we care about is living at height 1. So now we'll do the exact same thing over here. Exact same procedure. You have the same number of balls until you get down to contain I. And so now we've almost created sort of a path of balls where you can sort of compare one to the next and then so on, step our way along using this derivative estimate there. But these two towers don't quite connect up at the top. And so you'll need to add just one more, in fact. So if you go through this picture here, count everything carefully, you get the total number of balls. In this case, so we want 1/2 to the k times x ball, 1/2 to the k to be less than 1, and that k will be the number of balls we need. So equivalently, this is the same thing as saying that k is greater than or equal to the log base 2 of x. And so we need this many balls to go up, that many balls to go down again. So we have number of balls is 2 times natural log base 2 of x, then plus that one ball to connect the two of them. So instead of having order of x worth of steps, we have order of log x worth of steps. And the reason that that's good is because, well, now, as soon as we take C and iterate this claim here, we'll get this factor of c only occurring log x number of times. So it will become like x to some power. So by iterating applications of the claim, get that. So the thing we care about, so f prime at x plus I, this is less than or equal to some constant times, well, I'll call it c twiddle, times some constant c to the, so it's kind of subtle. Since we only care about order, it doesn't really matter that much. But if you think about it, for each ball, you need to have sort of two applications of the lemma. You have starting in the middle, then going to the intersection, then sort of intersection to middle, middle to intersection, and so on, just repeating that. So we'll apply it 4 times log base 2 of x plus 2 times. And then we get the derivative at I. Then you do the same thing over here. And so if you go through everything, you get the kind of bound you want. I'm not going to keep track of exactly what R is in this case, since this isn't even tight, this bound. So it's not, our proof isn't very strong here because we lost a lot in our choice of the path with balls here. But you get something of the form constant times, well, so let me write just the answer that we have and then explain why we get it. So So this is the answer we want, and we get that because, well, so it's clear that we get some power of x, right? Because there's c times, well, c raised to some multiple of log plus some constant term. But then the question is, why are we writing this sort of weird way, this x squared plus 1? And the answer is basically that if you sort of this naive analysis here didn't take into account the fact that the derivatives remain sort of nice even when x is very, very small. Right? If we just naively wrote down what this was, we get some constant times x to some power. So as x went to 0, like both these sides would go to 0. So we clearly did something wrong. And the answer is that in this sort of repeated application thing, we didn't take into account the fact that we have to apply the lemma at least once. And so by taking into account that we have to apply the lemma at least once, gives us these ones in our bound, giving us what we wanted. All right. So this is a method for sort of constructing bounds like this involving these derivatives that comes up a lot. Is you oftentimes want to sort of construct your bound by piecing together a sequence of balls, all of that are of radius 1/2 the imaginary part, and just sort of seeing where you can end up. All right, so that's exercise 4. And now let's go on to sort of our next favorite little theorem from complex analysis to apply, and that's sort of showing a quick application of how to use Bieber-Bach's theorem in producing bounds like with SLE. All right, so all right, so for those following along on the sort of exercise sheets, if you have them, this would be exercise 5. So first I'll remind you what the theorem is. So here's Bieber-Bach's theorem. And this is a theorem about sort of the growth of coefficients of an analytic function of one of these Schlicht functions like we had before. So we have a function on the unit disk, again. It's going to be Schlicht, so it's holomorphic. And also injective. And again, we put on the same normalization that f at 0 is 0, and f prime at 0 is equal to 1. And now we're going to write out f in terms of its Taylor series expansion. So we have that f at z is going to be, well, the constant term 0. Then we have z. So interesting things start happening when you get to the second one. So we have a2 z squared plus a3 z cubed, and so on. And what Bieber-Bach's theorem says is if you have a function, you expand it in its power series expansion like this, then the size of the nth term, the nth coefficient, is always less than or equal to n. Or sort of an equivalent way, if you want to sort of think in terms of derivatives rather than series coefficients, is that the nth derivative at 0 is always going to be less than or equal to n times n factorial. All right. So from this, we're going to want to conclude the following exercise. This is exercise 5. So for f mapping the upper half plane into C, so as before, injective, holomorphic, or I guess a shorthand term is you could call it univalent, but I don't want to throw on terminology without reason. So injective holomorphic function f. So for something of this form, then we have, for any z, that f prime of z, the second derivative of f at any point z is less than or equal to the first derivative at that point divided by the imaginary part of z, and there's a constant. So he tells you to find the best constant. I'll ruin the surprise. The best constant is 4. So I'll take a moment to erase the board so we have space, let you kind of ponder it. All right, so who thinks they see sort of the first step we're going to want to take here in our proof? So we have something that applies only for Schlicht functions, and instead we have this function that's defining the upper half plane. Here's a hint. It's the only trick we've used so far today. All right. Yeah, so we're going to want to look at the ball around the point. So you have z here, we want to deal with sort of a bound for any z, so we're going to put around it a ball of radius imaginary part of z. Same thing we did before. We want to sort of take our arbitrary injective holomorphic function in the upper half plane, build from it a Schlicht function, and the way to do that is just sort of cut out this ball around it and pretend our function is just defined there. And so we're going to want to construct exactly the same thing we did before. We want to turn this arbitrary function on this arbitrary ball into a Schlicht function on just the unit ball. So we're going to define g of w again. It's just going to be f at z plus imaginary part of z times w minus f at z over imaginary part of z times f prime at z. So this is exactly the same combination we did with the first problem. This is what takes our unit ball, maps it to this ball of radius imaginary part of z, and then applies f. And then normalizes everything. So we have f at 0 to be 0, and f prime at 0 to be 1. So since this is a Schlicht function, we know that this Bieber-Box theorem applies. And now, since we want to talk about the second derivative, we should talk about the second derivative here and the bound that Bieber-Box gives us, which is that Bieber-Box tells us that the, I should say, this here should have absolute values around it. And what it tells us here is that the second derivative of g at the point 0 is less than or equal to n times n factorial when n equals 2, also known as 4. And so now we calculate the second derivative of our function g. So up here we get out, so it becomes imaginary part of z times f prime of this whole thing. And then the second derivative will pull out the second copy of imaginary part of z. So this becomes imaginary part of z squared times f double prime of z. Now we're evaluating at the point w equals 0, so that's that. And the entire thing divided by imaginary part of z over times f prime of z. So that's what that center term is. And now, exactly as before, we'll just sort of isolate our f double prime of z, just multiply everything through. Some of these imz's cancel out. And you're left with f double prime at z is less than or equal to 4 times f prime at z, at z, divided by the imaginary part of z, which is what we wanted. So I know many of you are probably wondering like why we care about something like this, but there's a very good reason to sort of like things like this Bieber-Box theorem. And so while here it just sort of seems like a toy trick to get your second derivative to be less than or equal to some number times your first divided by the imaginary part, what this sort of means in practice is that oftentimes when you're doing bounds, like in the one for showing the existence of the curve, things like that, it will suffice to get bounds on the first derivative alone. Because the second derivative, by this Bieber-Box theorem, will always be better than the first derivative divided by imaginary part z. So if you have good control here, then you have decent enough control in the second derivative. And since Bieber-Box theorem just keeps on going, you have some vague control over the third derivative, fourth derivative, and everything. So you only need to really understand what happens to the first derivative in order to understand everything. And so that's what allows us to sort of push these estimates through, is because we can get control in these first derivatives. And thus, by sort of mechanisms of things like Bieber-Box or those original estimates we did before, get control on sort of all other derivatives, and then sort of handle everything we want about our function. All right, so how are we doing? 45. All right, so I guess, do people want to see more of things from the, since we have such a short amount of time, I'm going to have to skip quite a few problems around. And so do we want to see more things from sort of the estimates required to show existence of the curve, Or should we go on to talking about things involving the reverse Lerner flow and sort of things required to actually obtain the derivative estimates you need in order to do both the existence of the curve and all of the other bounds that we've been seeing so far afterwards. So I guess, is anyone really excited about doing curves, like showing the existence of the curve, filling out some details there? No. I'm guessing I get the same response if I ask the other question too, but let's do some things with some randomness in them. So bizarrely, so Greg has assigned very few problems with randomness actually in them, but we'll move to more random territory, I guess. So yeah, let's move past this existence of the curve stuff, because that'll all just be more purely deterministic bounds and everything. And so let's go move on to sort of questions about the reverse flow then. And that will have a tiny epsilon of randomness in it every so often. So before doing any sort of problems with the reverse flow, I think it's a good idea to sort of review quickly what the reverse flow is and what it means, since it went by very quickly when it was in lecture. So the definition. So the reverse Lerner flow is the solution to the time derivative of the function ht of z is a over vt minus ht of z, with the initial conditions that h0 of z equals z. And I'll just note that, well, I guess it doesn't matter since there's no paper copies, but this is wrong in the notes. He said ht of 0 equals 0, but that's gibberish. So this is what the reverse Lerner flow is. It's the solution to this. And this is very much like our forward Lerner equation, except we have this extra just sort of minus sign. We flip this thing around. And so, I mean, it's clear that this thing should have some sort of relationship to the forward Lerner flow. But exactly the nature of that relationship is a little bit harder to exactly identify. So here's sort of the quick and dirty intuition about things. So if you think about our Lerner flow and what that equation does, is it sort of at the point ut, so our Lerner flow, just as a reminder, it looks like this, and sort of in the time sort of dt, what this Lerner flow does is it sort of goes to the point ut and sort of pulls down a little curve of sort of capacity length dt above ut. And our reverse flow is exactly the same equation, except for this minus sign. So wherever before the forward flow was sort of pulling down a little curve of length dt, the reverse flow will sort of be pushing up a little curve of length dt at that point. And so this reverse flow is sort of growing a curve by pushing up little parts of it from the bottom, while gt is sort of creating the curve by sort of pulling down points and making it so it's not defined there. So if we want to sort of try and relate these things, we're going to have to look at something where we create the curve. And so gt inverse creates the curve. And so it creates it in the following way, sort of the following, I guess, order of things. So if you're looking at gt inverse at some different time, say gt1 inverse, gt2 inverse, gt3 inverse, so we're looking at sort of the images under these maps, the images of of the upper half plane under these maps. So at gt1, we will have sort of pushed up some little length of curve there. Up to time gt2, well, applying gt2 inverse will push up that little curve and some more, because gt sort of grows things from the tip, if you remember all the sort of stuff that's happened in von Sant's course, etc. And gt3, well, it just continues this pattern. It pushes up another segment of curve off the tip. And so, most importantly, sort of the parts of the curve that are grown already remain there. They remain sort of grown and in place. But now let's think sort of heuristically about what ht is doing. I mean, I haven't told you what it's going to be driven by yet, so this is all just sort of hand-waving. But ht pushes up curves from the bottom. So if we want to end with the same curve at time t3, what are we going to have to do? Well, I mean, we're just going to have to try and push up the same curve, but working from sort of the tip first and working our way back down. All right, so let's try and draw the same sort of pictures now for ht. All right. So we want to end up, in our minds, we want to have ht3 to sort of create the same curve. Something like that. Now, if we want to do that, we have to sort of, because it's pushing up from the bottom, we have to sort of grow it from the top part first. So whatever's going on here at, say, ht2, it should only sort of contain this top portion of the curve. So it's going to have to somehow be that top portion of the curve pushed up from the real axis. Because then as you evolve from here to here, you finally sort of push out that last part. And then ht1, well, it's going to have to create sort of this first little portion of the curve, whatever our driving function is going to be. We haven't defined it yet. And so I guess using the same sort of arrows as to keep track of where everything is, this becomes that top part, this part goes here, and this part goes here. And so the question then becomes, if we want to sort of relate h sub t to everything we did before, sort of how do you get this sort of behavior, pushing out the top part of the curve from these maps that we already understand, these g sub t's? So like, how would I produce that guy? So the first thing we clearly want to do is we want to create the whole curve. We take our gt inverse of t3. So to start there, so I'm going to try and sort of h at time t3. It should look something to the tune of taking first gt3 inverse to create the entire curve. And then you want to take this bottom part here and delete it. And that bottom part was gt of t1. So if you want to take whatever created that and map it back down, so you're left with only this part. And so that's a little bit wishy-washy because of these t1s and t3s. So like, what do we actually want? So let's fix some n time now, some time s. So t3 will be denoted by s. And I want to sort of create what h sub t should be. So, oh, oops. This actually was mislabeled here. That should be h sub t2. Sorry. So if you want to create now h sub t as sort of a process, what are we going to want to do? We want to take the entire curve, push it all the way up. So we're going to have to take g sub s inverse to create the whole curve. Then at time h sub t, we want to sort of have the whole curve minus that. So we want to have the whole curve minus everything except for the top sort of capacity t's worth. And the way that we get that is we go through and we subtract, then we delete the first s minus t's worth of the curve. Right? So if we want to, so we have a whole curve like this, say here it is at capacity time t, here it is at capacity time s minus t, and there's s. If we want to get what h sub t looks like, so that's the last capacity t's worth of the curve, well, we have to do exactly this. We have to create the whole curve, and then delete everything except for the last capacity t's worth of it. And so this kind of a long-winded explanation of what's happening with the reverse flow, but it helps motivate this next problem that sort of seems to come out of nowhere if you don't have this sort of motivation behind it, which is it makes precise this sort of relationship that I've vaguely outlined here. So here's exercise. This is exercise 10. And so I'll say let g sub t of z be a solution to the forward equation driven by u sub t. So we have our forward equation in mind. In fact, we're only going to really think about this forward equation from time 0 up to some fixed final time s. So driven by u sub t, I'll say for 0 less than or equal to t less than or equal to s. And now, similarly, we're going to have h sub t be a solution to the reverse equation. So let h sub t of z be a solution to the reverse equation driven by, and so it's going to be v sub t. We need to define what it is. So if you sort of think heuristically, you're going to want your driving function sort of near time 0 for your reverse flow to look a lot like the driving function for your original flow near the end. And so the right way to do that, so you start at time, so the driving function starts at 0, turns out to be, you want it to become, want to make sure I get the sign right, u sub s minus t minus u sub s. So sort of look at the driving function near the end. Then what we're going to get is a relationship pretty much like this with just a few constants and shifts thrown in. We're going to get that then h sub t of s equals g sub t, so g sub s minus t, sorry, it's h sub t of z. So it's g sub s minus t composed with g inverse of s. And now I ignored all the shifts over there, but what turns out to work is z plus u sub s, then minus u sub s. And so currently this is, again, I apologize, a deterministic fact. So still no randomness has occurred, but it is what the problems are. So here it is. H sub t of z is this composition. And so seeing why this is true was going to be simple enough, because so we know that h sub t of z satisfies some nice differential equation, this reverse flow here. So if we can just show that this side over here satisfies the same differential equation with the same initial conditions, by uniqueness we'll be done. So so here's our proof of it. We're going to let h sub t tilde of z be this thing, g sub s minus t composed with g sub s inverse of, well, I'll write it, z plus u sub s minus u sub s. So we have this whole composition of functions here. Now we want to show that it satisfies the same equation. So the first thing to note is that h sub t tilde of, sorry, h sub 0 tilde of z, well, that's g sub s composed with g sub s inverse. They just go away, so it's z plus u sub s minus u sub s, they'll go away. And so you're left with just z. So the same initial conditions as before. And then Now if we try and take the differential equation of it, so we look at dt of h sub t z tilde, well, it's dt of this beast here, but it's not actually that bad because the only place t occurs is in this one application here of the Louvre equation. Everything else is at this fixed time s. And so we get that this just satisfies the Louvre equation, so a over gs minus t composed gs inverse z plus us, then minus the driving function at the time s minus t, the use of s minus t. And then from the chain rule here on this s minus t, we get an extra minus sign. And now, in order to make this look like h tilde again, we have to add in effect, we have to subtract the u sub s and add a u sub s. This becomes minus a over g sub s minus t composed with g sub s inverse of all that stuff, minus u sub s plus u sub s minus u sub s minus t. But now we're sort of in luck because that's just our original ht tilde. And so simplifying things a bit, we get a over, so u sub s minus t minus u sub s minus h sub t tilde of z. But now we sort of recognize, lo and behold, this is our driving function v sub t. And so equals a over v sub t minus h sub t tilde of z. And so it's the exact same equation that our reverse flow satisfied. And so this is exactly the relationship between the forward flow and the reverse flow. All right, and so we'd like to relate this back to sort of properties of what we care about, the Schramm-Louvre evolution. So let's sort of look at a slightly specific case of this. All right, so let's look at the specific case where t equals s, what it tells us there. So when t equals s, this tells us that h sub s of z, this g sub s minus t here just vanishes. We get this the same thing as g sub s inverse of z plus us minus u sub s, or sort of equivalently in notation as he defined earlier. This thing here has a name. This is f sub s of z, then minus u sub s. And this is the thing that we always want to be able to understand and control, this f sub s of z. Because this is what, well, in the existence of the curve, this is what gave us sort of all the derivative bounds we needed. And in everything that's following, this is sort of the main thing we use for estimating, is trying to understand this f sub s. And it normally has a much harder to use differential equation, but by this, there's sort of, we can relate it to the h sub s's, which are easier. And now, I guess, the corollary, which is stated in class, but which I'll state here again just because it's why we want this fact at all. So if u sub t is a Brownian motion, and I guess, and g sub t is a solution to the forward equation, driven by u sub t. So we have our standard Schramm-Louvre evolution now going forward. And now if we drive our reverse equation by also a Brownian motion, so and v sub t is a, so I guess I should have said standard Brownian motion here. So again, standard Brownian motion here. And I'll say and h sub t is a solution to the backwards equation driven by v sub t. So all the same things just going backwards now. Then h sub t of z is going to be equal in distribution to, well, g sub t of z inverse, z plus u sub t minus u sub t. So to understand this fellow, we only need to understand this fellow when he's driven by a Brownian motion. And that'll be much simpler formally to work with. All right, and so if we want to work with this, we're going to have to try and sort of find some ways we can simplify computations with it. And sort of always the best way to simplify computations with things is to find some sort of symmetry that you can exploit. And so in the forward equation, we had a nice scaling relationship. And in the reverse equation, we will have another scaling relationship as well, which we'll make explicit in this problem. So this, I believe, is exercise 12 now. And so what this states is the following. So let h sub t of z be a solution to the reverse flow driven by Brownian motion, standard Brownian motion. Then we have the following scaling relationship, that 1 over r times h sub r squared t at rz. So this is for any r. This will be equal in distribution to h sub tz itself. And then the important consequence we get from this in terms of our desire to understand derivatives is that, well, h sub r squared t at rz prime is equal in distribution to h sub t at z prime. That's just obtained by differentiating the line above. All right, so all right, so we want to show this scaling relationship. And all we have is that satisfies this reverse derivative flow driven by Brownian motion. So does anyone know sort of what we're going to have to use here if we're going to want to prove this, since all we have is the Brownian motion to play with? So it's going to be Brownian scaling, right? Brownian scaling is the only relationship we have that looks even vaguely like that. And if you see, we sort of have it built in there. We have that t, squared factor in the time scaling. That would sort of make sense for finding Brownian scaling somehow in this. All right, so let's think about proving this. And well, again, there's only like one trick we have. We have the trick where you can sort of take this and then try and differentiate this in time and see what equation we get out of it, and see if we can sort of shift it around to become a form that's useful to us. So I'm going to let h sub t tilde of z be h sub, so 1 over r times r squared t rz. So there's that. Now let's look at the time derivative of h sub t z tilde. Well, I mean, right here we just take the time derivative, so we have our 1 over r, then we get a r squared from the chain rule. This satisfies the reverse Lerner flow, so it's a over v sub t minus h sub r, v sub r squared t. You always need to make sure that your driving parameter is at the right time, minus h sub r squared t times rz, well, at rz. And now we can take this factor of r that's out front, just move it down in the denominator. We got this is a over 1 over r times v r squared t minus 1 over r h sub r squared t of rz. And now this, by Brownian scaling, is, well, we have a over, let's call it vt tilde, minus this is h tilde tz, where by scaling, vt tilde is a standard Brownian motion again. And so it's driven by the same process in law, and so this implies, I guess, what we want. It implies that the two solutions have to be equal in law as well. All right, and so we have this nice symmetry that will allow us to sort of scale away things we don't like when we're working with estimates. Like if we have, say, if they were at 2 different times, we can, up to in distribution, rescale it so that the times are the same, and we're instead looking at different points. So this will allow us to compare turn comparing solutions at 2 different times into comparing solutions at the same time, at which point we can start using our normal conformal map estimates that we derived earlier on in this lecture. All right, and so this leads us to the thing he called the, what was it? It was a parabolic, whatever it was, estimate. I don't remember what he called it. The parabolic Harnack inequality. So this is exercise 11 now, taking one step backwards in our problems. And so what this asks us to prove is the following. So for any v contained in H, so any subset of the upper half plane where v is now compact, and for any s naught greater than or equal to 1, there exists 2 universal constants, C1 and C2, such that, so for all t greater than or equal to 1, we have the following inequality. It will be that C1 to the lambda times expectation of h t prime at I to the lambda is less than or equal to the expectation of h s t prime at z to the lambda, which is less than or equal to C2 to the lambda times the expectation of h t prime at I to the lambda. So this, this is for all s between s naught inverse and s naught, and for all z in our compact set V. Simultaneously for all those, universal across all, well, across H, where H is a solution to our Lerner flow. All right, and so the reason bounds like this are useful is because, I mean, we've now taken this entire compact domain, any derivative anywhere in that compact domain, and over some, think about this as like some large period of time here. What does it look like? Well, the derivative never looks much worse than some constant times the derivative at some fixed time at some fixed point I. And also it's bounded below by the same thing. So we're able to take many times, many places, what the derivative looks like and reduce it down to a single one. So the key to this will be an application of the scaling rule we just showed. So again, I'll erase the board. And we'll see what we can say. All right. So as I said, we're going to want to be using the scaling relationship. And there's sort of only one place in this equation we can apply scaling. And that's here. Because, well, I guess we can apply it to the other terms too, but there's one place that makes the most sense to apply scaling, which is to apply it here to get rid of this factor of s. And so we know that from our previous problem that h sub st of z prime, this quantity here, this will be equal in distribution, well, to what we got at the end there, which is simply, so you need to make sure that you follow everything back correctly. So ht prime at z divided by square root of s. I think assuming I got the scaling relationship right. It might be the other way around, but it actually really doesn't matter at all in the argument we're going to do. All that matters is we can sort of push that factor s onto the z and off of the time t. And so the reason we want to do that is because, of course, this implies now that the expectations are the same. And so we've sort of reduced down this question here, this parabolic Harnack inequality, instead of being about different times, to the same time. And in fact, because everything here is expectations, we could even just sort of use them as if it were the same equation. So now I'm going to do one simplification to sort of reduce this problem down to something that's easy to keep track of. So I'm going to call this z over square root of s, I'm going to give this a name w. So before, what we had was that we had that z was in this compact set V, and s was somewhere between s naught inverse and s naught. And so these two things combine together to mean that w is somewhere within, well, the union over all s between s naught inverse and s naught of 1 over the square root of s times our compact set V, just sort of dilating by that. And whatever this is, doesn't really matter. I'm going to call it W. It's another compact set. That's all we're going to need from it. And so we've reduced it down to the following. So it suffices to show for all t and all w in some other compact set w. So compact, that the expectation, sorry, C1 to the lambda times the expectation of ht prime at I to the lambda is less than or equal to the expectation of now ht prime at this point w in our compact set to the lambda, and less than or equal to c2 to the lambda times expectation of this same quantity again, so ht prime at I to the lambda. All right, so I've taken and I've sort of scaled away the different time in the middle. But now if we look at this, this looks an awful lot like those deterministic bounds we got earlier. So I mean, we have all these expectations here. We always think that would help us. But now that we've sort of scaled it to the same time, we at least feel like we might be able to prove it just without the expectations there at all. It might just be a deterministic fact. So it would suffice to show that c1 to the lambda times ht prime at I to the lambda less than or equal to ht prime at w to the lambda less than or equal to c2 times ht prime at I to the lambda. And now, oh, sorry, there should be a c2 to the lambda here. And now, of course, now that we've written out as a deterministic fact, all these lambdas are just sort of cluttering up our equation. They don't do anything anymore. So this is exactly the same thing as saying that we can find c1 such that ht prime at I, well, let's find c1 and c2 such that c1 times ht prime of I is less than or equal to ht prime at w less than or equal to c2 times ht prime at I. It's exactly the sort of familiar derivative estimates we were doing before. So what's this look like in a picture? If we take our upper half plane, we have our compact set, which is called W. And then somewhere else, we have our point I. So now we want to say that the derivative anywhere in here in W is comparable to I. And we have only one trick for doing that sort of thing, and that's this method of putting in on balls of radius 1/2 times the imaginary part. So let's try and do that again. Since W is compact, we may cover it by a finite number of balls of the form that we like. So balls like ball of radius imaginary part of z over 2 about z. So in the picture, that's something like this. We have a whole bunch of them down here. If you get higher up, you need fewer. And then they get really big up there. So there's our finite number of balls covering our set W. Now we want to relate it to I. So we need to connect I up to that set. And so we're going to take some finite number of balls just going from I to our compact set. You can clearly do that as well if you want, because the curve between I and that compact set is compacted as well. So I guess and add balls to connect W to I. So now we can get the bound we want simply because the number of balls we chose here was completely independent of what point we have inside this compact set. It's some fixed number that depends only on the compact set itself. And so by our lemma that we had way back at the beginning, we can say that the derivative at some point in the center, so yeah, of h sub t prime at some point W in our compact set is always going to be less than or equal to that constant we had at the beginning, raised to the power, well, number of balls in the picture, times ht prime with I, and greater than or equal to c to the minus number of balls times ht prime with I again. Simply because if you want to get from I to any point, well, you just sort of go along some number of balls, and you never need to use more than the number of balls you have. So putting this all together, this is not just some constant that depends only on the domain. We have that there's, well, there exists C1 and C2 as desired. All right, and so I guess that's feeling like the time to stop. So that's all that we're going to be able to cover here today. Greg has many, many more problems in his problem set. This gets us only sort of part of the way through the problems he assigned for lecture 2. So if you have any questions about any of the other problems or want to know anything about it, just sort of come find me somewhere, I don't know, buy me a Caparini or something, and we can talk about the rest of the problems or whatever. So that's all. Thank you. Yes. Any questions either? Before? All right. Yeah, that's all.